Welcome back, everyone. This week we are starting a new unit on systems of equations. And the first thing that we're going to do is talk about how to solve a system of equations by graphing. We're not going to go over what a system of equations is because we should remember what that is from intermediate algebra. If you don't remember what that is, hopefully this page will help give you a little bit of background about what a system of equations is. So take a minute to read through this and pay particular attention to the very bottom of the page with the three graphs there, because that gives you information about the three different types of solutions we can get when we solve a system of equations. And when you're ready, continue on and we'll go through some examples. All right, the first thing we have to do is be able to determine if a point is a solution to a system of equations. And the simplest way to do it is to just take the point and plug it into each one of the equations. And if both equations end up being true, then we know the point is a solution to the system of equations. And I'll show you what I'm talking about just by doing this one. So the first equation, we have 2x minus 3y equals 6. So what we need to do is just take the x and y from our ordered pair here and plug them in to our equation. So we have 2 times 12 minus 3 times 6 equals 6. So if we simplify this, we have 24 minus 18 equals 6. So we have 6 is equal to 6. And when I say true, what I mean is if what we get at the end is true, well, 6 is equal to 6, so we know that's true. So I can go ahead and put a check mark next to that one. The second one, we have x is equal to 2y. So I'm going to do the same thing. I'm going to plug in my x, plug in my y. So I have 12 is equal to 2 times 6. So 12 is equal to 12. And again, that one is true. And since both of them are true, I can come back up here and say, yes, this point is a solution to that system of equations. Okay, so the key thing is to just look for whether both of the equations are equal on either side, and you'll notice that in this case, the red example, it ended up with 6 is equal to 6. The blue example, it ended up with 12 is equal to 12, and that's okay to have different numbers, but as long as you don't have different numbers in the same equation, that's okay. So they don't have to both be 6 is equal to 6 or 12 is equal to 12. They just need to be equal. All right, the next thing we want to talk about is really the point of this whole lesson, is how to solve a system of equations by graphing. And if you remember, we just finished talking about graphing, and we talked about graphing equations like this that are in standard form using a table or using x and y intercepts. And we could do that, but it's not going to give us enough information or enough useful information to be able to actually find the solution very easily. So what we have to do is go back to a method that we learned in intermediate algebra where we use slope-intercept form, and we would take the y-intercept and plot it, and then we would take the slope to find more points. Okay, so the first thing we have to do with these equations then is convert them to slope-intercept form. So the first one, we have x minus 3y equals 9. So basically what I want to do is just solve this for y. So I need to get everything that's next to the y out of there. And the first thing I want to do is subtract x from both sides. So I'm going to subtract x, and then I'm going to write it in the right order for y equals mx plus b. So when I subtract x, it becomes negative x. So I have negative x plus 9. Now, I didn't show the work that goes on in between those two lines, but normally we would write minus x, and then we would be able to see what we're doing. And then we have to divide by negative 3, so everything is going to get divided by negative 3, so I end up with y equals negative x over negative 3 minus 3. And the negative x over negative 3 is a good example to start with because it's kind of different. We don't normally see stuff like that, but if we remember, this numerator is actually a negative 1x. And anytime we have something that looks like a fraction like this, we can move that variable to the side, and those two negatives cancel each other out. So what this ends up becoming is y is equal to 1/3 x minus 3. And so then I can go ahead and graph this by first plotting my y-intercept. So my y-intercept is -3, so I'm going to go down to -3 and make a point. And then I'm going to use my slope. My slope is 1/3, and if you remember from intermediate algebra, the 1/3 tells us, the top number tells us to go up or down, and the bottom number tells us to go to the right. So in this case it's positive, so that means up, so we're going to go up 1 and over 3 and make a point. And we're just going to keep doing that. And this is where some people might be like, well, why do I have to keep doing this? Well, there's a reason for it. And the reason is because we're going to plot another line on here, and we don't know where that line is going to cross this one. So for the first line, I want you to just make sure you plot every single point you possibly can, because we don't know where that second line is going to come through, and what we're looking for is the point where they intersect. And if we don't have all these points over here, it's going to be hard to tell exactly where it does intersect that line. Okay, so I just graphed the first line, and the second one, we have x plus y equals 1. This one's a little bit simpler, so all we have to do is subtract x from both sides, so we have y equals -x plus 1. And remember, ideally we have our slope as a fraction. Well, there's no slope, there's no number there, but we know there's a 1 there, so there's a -1, and then we can always put it over 1. So our slope is -1 over 1. Our y-intercept is +1. And notice when I highlight that y-intercept, I always highlight the sign as well, because we don't want to forget that sign. In this case, it's +1, so it doesn't matter. We would probably make a mistake and say, oh, it's +1. Well, that's a good mistake. But in the first one, if we only highlighted the 3, we might say that's +3, and that wouldn't be good because the minus sign makes it -3. And then we're going to go ahead and graph this. So we start at +1, and then our slope is telling us to go down 1 and over 1. So I'm going to make a bunch of points. And I can stop when I hit that first line I graphed. And this one was relatively simple because it was pretty quick. And we can see that the solution is where the blue line runs into the red one, or where they intersect. And so I can just look at that and say, all right, my x value is 3, my y value is -2, so my solution is 3, -2. And if we had more space, what we could do is go back up and actually plug this in to both of the equations, like we did on the previous example, to confirm that it is the solution to this system of equations. All right, here's another example. Similar to the first one, we have one equation that's in standard form, one that is in no form that we're aware of, because it doesn't have a name, at least. It's just an equation. So the first one, we have 2x plus y equals 7. So I'm going to subtract 2x from both sides, so I end up with y equals -2x plus 7. And I'm good with that one because the y was all by itself to begin with. So again, the y-intercept, the slope, probably ought to add that 1 underneath the slope so we remember it's a fraction. So I'm going to go up to 7, make a point, and then I'm going down 2 over 1. And again, I know it might seem kind of annoying, but for the first one, always graph as many points as you can. And I got to go back the other direction just once. Nice. Notability straightened my line for me. All right, the second one, 2y equals negative 4x. So we can graph this. Well, first we have to convert it to slope-intercept form. So we just have to divide everything by 2. So we have y equals negative 2x. And there's no y-intercept. There just isn't a number there. So the one thing we can add that isn't going to change anything would be 0. So that's our y-intercept. And hopefully you're noticing something about these two equations, about their slopes. So they have the same slope. So that means those two lines are parallel. And if two lines are parallel, we know that they're never going to cross. But we can go ahead and graph a little bit of it. So in this case, I don't need to do a whole bunch. So I just went down 2 over 1. It's the same thing. And so I can go ahead and graph that. And you can see that those two lines are parallel and they're never going to cross. So if they're never going to cross, we know that the solution to this is no solution. Okay, so anytime you see two lines with the same slope and different y-intercepts, they are never going to cross because they're parallel, so we would say they have no solution. All right, the last example, maybe you can guess what's going to happen here. First equation, we have x minus y equals 3. I'm going to subtract x from both sides, so I have negative y equals negative x plus 3. And then divide by negative 1, and when I do that, everything just changes signs. So I have y equals x minus 3. All right, so I'm not even going to bother to graph this one yet. I'm going to do the other equation first. So, and hopefully you might start to do the same thing, because you can make your life a little easier if you do this. So then we have negative 2x plus 2y equals negative 6. And then everything gets divided by 2 in this case. So we have negative x plus y equals negative 3. And then I'm going to add x to both sides, so I end up with y equals x minus 3. And we should notice that this equation and this equation are exactly the same. If they are exactly the same, when we graph them, they're just going to be on top of each other. So I'm not even going to bother graphing them, because I know that if those two equations are exactly the same and they're sitting on top of each other, that means we have an infinite number of solutions. So we can say infinite. So there you go, 3 different examples of the 3 types of solutions that we can get when we solve a system of equations by graphing.